Alright, so let's continue with our study of electromagnetic waves. In this video, we're just going to go over some of the general characteristics of the electromagnetic waves that are predicted by Maxwell's equations. So just to remind you, in the last video, we went over the idea or the fact that we can summarize all the electromagnetic phenomena that we studied so far this semester into 4 basic equations, which are now known as Maxwell's equations. We also saw that 2 of those equations basically predict the existence of electromagnetic waves, which sometimes we refer to as electromagnetic radiation, sometimes we refer to it as light, and sometimes we refer to it as electromagnetic waves. So we talked a little bit about how these waves are generated. Some of the math involved in this, seeing how this happens, is a little bit past what we are expected to know in this course, and so we're not going to go into a lot of the details about it. And then also, now coming up is we're going to talk about today just some of the basics about these electromagnetic waves, including how we might describe them. The last item on this list is going to be covered in the last video, so not in this one. So just as a review, these were Maxwell's equations, and this is basically trying to summarize the material we've been studying since the beginning of the semester. And if we look at those last 2 equations, in the absence of any charge distributions or conducting current, we can see that if you have an alternating current, like a power line, which is also could be described as a vibrating charge, you can actually say through these 2 equations, Faraday's law and Ampere's law, that the vibrating charge will produce a magnetic field, which is going to be changing in time because the electric field that it is based on is changing in time because it's vibrating. Then what happens is that magnetic field creates its own electric field, and that's coming from Ampere's law. And it just keeps going back and forth and back and forth. Notice the orientation of the fields and the electric field and the magnetic field. But this is the idea of how these electromagnetic waves can be made and how they're going to move through space. And notice that they can each generate the other. Magnetic fields generate electric fields and vice versa. And this is part of the reason why we don't need any sort of material, any medium for the waves to travel through. When we studied waves at the beginning of the semester, we talked about water waves or waves traveling in a string, things like this. They needed a medium to travel through. But electromagnetic waves can actually travel through a vacuum. So this is what our electromagnetic wave might look like because of the fact that it's changing with time and also is traveling in space. We can describe the electric fields and the magnetic fields as sinusoidal waves. If you remember, we saw that the loops that we were using to represent electric fields and magnetic fields were oriented perpendicular to each other, and we see also in this picture that the electric field and the magnetic field are oriented in different planes, and they're perpendicular to each other. And finally, they are both perpendicular to the direction of propagation. We can see all this mathematically in those equations, but again, we're going to do a little bit of hand waving and try to be satisfied with just some general knowledge without getting into the specifics of the math. I do want to just kind of describe for you what happens with the Ampere's law and Faraday's law. If we manipulate it, it basically comes down to what we call the wave equation falls out of those expressions. The wave equation in general has this form, and this is a really important equation in physics that has the general form of, that I'm writing down right here. So it's like the second partial derivative of some quantity with respect to x, and then it's related to the second derivative of that quantity with respect to t. And then this right here, I wrote as 1 over c squared. In general, I actually should have written it as 1 over v squared. So what it is it's the equation, the partial differential equation that is for waves, because of course, remember, a wave varies not only in position but also in time, and also a wave travels with a particular speed. So the more general form, I should have used the 1 over v squared, but for light, of course, this is the speed of light, and that's what we see when we look at specifically the Maxwell's equations give us two results. We see that the electric field satisfies, which is in a y directed, it's in the y plane, satisfies the wave equation. We also can see that the magnetic field would also satisfy the wave equation, where the magnetic field is has a z component. And for both of those, this means that the solution has the form of a sinusoidal wave, which we see right here. That should look sort of familiar. We did study waves right at the very, very beginning of the semester. And again, this represents 1 over the speed of light squared. And we'll take a look at that later. So I know that they try to sort of convince you that these electric fields and magnetic fields satisfy this wave equation in the chapter. It's good to read through it to try to follow their logic. It is much easier to get that out of it if we use some upper level math, but we're just not going to do that right now. And so what I want you to do is just kind of generally feel comfortable with the facts and not feel that you have to derive it on your own. There's two things that are also relevant that we find true about the magnetic fields, is that the maximum magnitude of the electric and magnetic fields has the ratio of E to B is always going to be the speed of light. And as you might have gathered from that wave equation and what I told you about how it's related to velocity, we find that the speed of light is related to these constants that we've run into, the permittivity of space. So that gives you, actually, if you put in the values that we've learned for these two constants and put it into that equation, you'll find that it's the speed of light, which is like 2.99 times 10 to the 9th, I think. So that's true. We also, we call the electromagnetic wave, we're just going to assume it's just a plain electromagnetic wave, which basically means as the wave is traveling through space, we can kind of think of the wave front is like just a plane where you can look at the electric field and the magnetic field lie in that plane. They are perpendicular to each other, and they're traveling here. The electric field goes in the y direction. It varies along the yx plane. The magnetic field varies along the zx plane. And of course, because of that, they are perpendicular to each other, and they're also perpendicular to the direction of propagation, which is given by the speed of light. And that arrow tells you the direction of propagation, which means the direction that the wave is moving in. One last little fact that we're going to use in the final video of this chapter is that another fact about the electromagnetic wave is if you do the cross product of the electric field with the magnetic field, it gives you the direction of propagation or the direction of the speed of the wave. And again, that's something that we'll use when we look at something called the Poynting vector and when we talk about the flow of energy as the wave moves through space. Here again is just another picture, sort of reviewing what the electric fields and the magnetic fields look like. This one maybe it's not as obvious that the magnetic field is in a plane perpendicular to that of where the electric field is in, but also we see these are the ways that we might express the electric field, where E naught and B naught are the magnitudes, sort of the amplitudes of the wave, and then of course we remember the wave number K and the angular frequency omega. Reminding ourselves again that we can find the speed of the wave, remember, was related to omega and the wave number, and again here is the ratio of the electric field to the magnetic field will always give you the speed of light. That's something we'll use in the later video as well. And now for the last thing is I just wanted to go over in general, what do we mean by electromagnetic radiation? I think one of the points of confusion is because we often, when we think of light, we only think of light that we can see. But it turns out that light that we can see is just one category of electromagnetic radiation. And so we might not have ever made a link between things like ultraviolet radiation or X-rays or gamma rays and the light that we can see. So all of these are considered electromagnetic radiation. What makes them similar is that they're all predicted by Maxwell's equations. They all consist of electric and magnetic fields that are varying with time and traveling as waves. And they all travel with the speed of light. So then you might say, okay, well, why are they different from each other? The thing that makes them different from each other is that they all will have different wavelengths and frequencies. So along the electromagnetic spectrum, everything is traveling with the speed of light, but you can make the speed of light with different combinations of wavelength and frequency. So you can have a very high frequency and a short wavelength, or you can have a very long wavelength and a low frequency, and these are still going to travel at the speed of light. So often we sort of order them in their order as they go from one end of the wavelength spectrum to the other, or we order them by frequency. In this picture they show sort of the variation for both. So as we start at the left, we're looking at radio waves, which have relatively long wavelengths, but if we look at their frequency, they're relatively low. I know 10 to the 4 is a big number, but if you look to the right, you see the numbers are getting even bigger. And so as we go from radio waves to microwaves, we see that's what's happening is the wavelengths are getting shorter and the frequencies are getting higher. We go to infrared, which is getting even a shorter wavelength and a higher frequency. Finally, we get to the visible part of the spectrum. If we pass that into ultraviolet, we see that the wavelengths are getting even shorter, the frequencies are getting higher, and then as we continue to X-rays and gamma rays, we see even shorter wavelengths and higher frequencies. And so this whole band of different types of electromagnetic radiation is called the electromagnetic spectrum. Just focusing on the visible part, if you have a scale, is a very small sliver of the entire spectrum, but it's just particular wavelengths and frequencies that we can detect with our naked eye. And we usually say in a very general way, as your book points out, the boundaries between different types of radiation is not like a sharp boundary, but sort of a soft, fuzzy boundary. But in general, we sort of like to say that visible light goes from about 400 nanometers to 700 nanometers. Violet being the shorter end of the shorter wavelengths, higher frequencies. Red light being the longer wavelengths and lower frequencies. Okay, so that's it for this video, just giving you some basic background information about electromagnetic waves.